Welcome to our NPTEL lectures on power quality improvement technique. Today we are going to discuss about improvement of the power factor rather by improvement of the power factor by capacitor the capacitor bank, but what is implication of the capacitor also in the other entities, that also we require to discuss. While discussing the standard, we have discussed that switching on and the switching off the capacitor bank has its implications on the power other part of the power quality apart from correcting the power factor. So, we shall discuss in detail, that is selections of the power factor correction capacitor for the industrial and the large commercial users. Now, we shall discuss about the power factor fundamentals that we are always aware of it, but we have to start with that. The need for the power factor corrections, we know that why we require the power factor correction, otherwise we require to take more current, effect of the harmonics and the total power factor and the displacement power factor, corrections of the correction or alternatives and the capacitors locations. Thereafter, we shall see that capacitor sizing and the return to the investment, return on the investment, capacitor application to the motor, capacitor switching equipment, and we shall see thereafter steady state VAR and the dynamic corrections and the standard and the code. So, most of the plant loads are inductive. So, we have a predominantly induction machines and require a magnetic field to operate. These are motors, transformer and the fluorescent lighting. The magnetic field is necessary, but produce no useful work. So, that is the magnetic part of the current. The utility must supply the power to produce the magnetic field and the power to produce the useful work, pay for it all. So, you require to pay for the both. This type of the current are the active and thus have active and the reactive components of the current. So, you know all, that is the active power, that is in the kilowatt, and this is the reactive power, and ultimately you will be charged to based on the kVA, not the active power. Thus, if you reduce this hypotenuse, this perpendicular, ultimately then you will be paid only for active power. So, it makes sense to reduce this part of the component. So, power factor, a measurement of efficiency. The ratio of active power to the total power, that is you all know, ultimately it is a cosine, and sometime in the case of the power electronics we will see that there is another term, there is a displacement power factor. The power factor reading close to 1 means the electrical power is being utilized effectively, while low power factor indicates that poor utilizations of the electrical power, most of the power is wasted in the magnetics. So, for this reason, this is we can have a leading and lagging power factor, this is inductor, and for this reason you have a capacitor, we can have a load. So, for this reason we require to correct the load, and we can have a resonance condition when capacitive VAR and the inductive VAR are matches each other, and thus system behaves as a resistive circuit. Now, you see that industry uses different components, industry as well as we ourselves, and what is the power factor of it? Auto parts, that is power factor of 0.7 of 7 to 80, and that is air compressor. So, thereafter cement 80 to 85% hermetic motor, and that are clothing it may be very low, it is 35 to 60. Thereafter electropetting, it is 60 to 70 and so on, and we have different kind of waving, individual drive, standard speed, high speed for the stamping, for melting arc furnace, inductance furnace 50 or 60 hertz both. So, we will have this overall power factor problem, and these are all industrial uses. You can see that average power factor is in between of 0.75, 0.65, even arc welding is 0.35. So, for this reason we require to do something to improve the power factor, that is also a issue of the power quality. So, this is the kilowatt, and ultimately if you have to generate the lagging power factor, that is the kilowatt and the kilowatt hour you will fit. But instead of that, you can have a over excited synchronous generator, kilowatt and kVA, it is coming in this direction leading, and thus this can be, but for problem is that you operate by the mechanical power, real power is been wasted by this synchronous generator, so that it generates the capacitive bar. Instead of that, why can't we have a static device to generate the capacitive bar? This is the motor load characteristics, this is a percentage of the power factor, that is power factor 1 is marked as 100%, and you can see that this is a motor load, and this is the power factor with the capacitor, and we can almost get 100% or 1 power factor, and it is the motor power factor without capacitor. And so, this is a red one, and blue one is a kVA, and according to the loading it will improve, and of course, the straight line is the real power watt, and you can see that this one is a kVA. kVA is quite high in the lower rating when it is not loaded, percentage of it. So, when it is not loaded, predominantly it will be generating the inductive bar, and one solution can be given by the power factor with the capacitors. So, in industrial facilities, mostly we have induction motors loads, energy efficient motors not optimized for the PF. So, we can that generate the low power factor. Low power factor caused by oversize of the light loaded induction motor. When you are loaded that machine properly, it will take good power factor, but if you are not loading it, predominantly it will have a magnetizing component, and thus it will degrade the power factor. Power factor has so many problems. So, low power factor results in the poor electrical efficiency, higher utility bills, lower system capacity on the supply side, generation capacity and the line losses. Apart from that, power factor corrections capacitors provide an economical means to provide the improving the energy efficiency. That is one of the greatest merit of this entity. So, for example, you take it power supply, you require you essentially require 8 kilowatt of power, and ultimately you also send your system is loaded because current has to flow through it, voltage is constant. Also 600 kVA, or overall kVA is definitely 10,000, and ultimately you get power factor of 0.8. On the other hand, if you have this capacitor bank of 4000 bar, then what will happen, this power will sink, this capacitor bar will supply the power, ultimately net kVAR coming from the line is 2 kilowatt. So, overall if you square it up, that kVA rating will be 8250 and you got a 97% of the power factor. Thus, this power handling capability of this line has been comprehensively increased. So, you can overload it further for the real power. So, that is an example. So, demand reduces to 8250 from 10 kVA, from 10,000 kVA, and thus what happened. So, this much 1750 kVA transformer capacity has been released due to that, and power factor was improved to 80% to 97%. So, there is another few issues, and that is with the harmonics, mainly in power electronics, that is displacement power factor, total power factor, the effect of the harmonics on the capacitor. These are the few entities we require to be discussed now. So, till now we have talking about the linear load. Until recently, most electrical equipment draw the current in linear fashion from the linear voltage. This is a voltage and current, it may have a phase lag or phase lead depending on the current is inductive or capacitive. But current and voltage are both the sinusoidal, but you can see nowadays because of the nonlinear load at stable speed drive, voltage and current are far from the sinusoidal and they are nonlinear and current is not sinusoidal. So, it is because of the nonlinear current. For example, computer comes with SMPS. SMPS is essentially a AC to DC conversion, thereafter DC to DC conversion, and DC to DC conversion definitely has a rectifications. This rectification is a nonlinear conversion, and thus it causes the injection of the harmonics. Same way for the fax machine, same way for the photocopy machines, copiers, or the variable frequency drive, V by F control drive, or you may have a electronic ballast, that is for the chokes, and almost any electronic component generally require a DC supply, regulated DC supply, and thus you require to convert DC to AC to DC, and you put or inject the high harmonics. So, this is the way actually you can see. So, in case of the 50 hertz or the 60 hertz supply, this is the fundamental, and you will have a frequency like this, and if you have it is 360. If you have 50 hertz or third harmonic, that will be though it will be a cophasor for the 60 hertz or 50 hertz. So, it will be shifted here. Similarly, you will have a fifth harmonic that will be either 250 or the 300 hertz. So, that will be something like this. Similarly, 350 or 420 hertz, that will be something like this, and ultimately whatever the waveform you have shown here, this it can be think of, you can see that you just add up this waveform and ultimately you constitute this waveform. So, you have some portion of the fundamental, some portion of third, some portion of fifth, and some portion of the seventh harmonic, so that you get this kind of the peaky current. So, this is called, so we require to define another term, that is the distortion factor. So, total power factor or DPF, that is a harm coefficient, sometime we say, that is DPF equal to Kw by Ka, it is cos phi, and thus the harmonic coefficient will be 1 by 1 plus Th d square, where TPF is the total or the 2 power factor, DPF is the displacement power factor, the harm coefficient or the harmonic factors is given by the cos delta. Now, for the variable frequency drive, this is abbreviation of the FFD, and displacement power factor is 0.9, and for the THD may be 90%, the harmonic coefficient you can calculate, you will be 0.743. Thus, you multiply effective power factor or the total power factor will be 0.7061. So, we require to put the capacitor, I have told you, to mitigate the reactive power problem, but if it is there, the adjustable speed drive, then there will be a lot of disadvantage. So, placing of this capacitor when you have this adjustable speed drive, then there is a problem. For example, you see that this is the transformer, from there power is coming, and there is a one entity that is a variable frequency drive, and ultimately it is a harmonic source, and there is a another machines. And what happened, since it is a high frequency, so high frequency will get the path through the capacitor. So, drives present anywhere, the harmonic current they produce can flow back to the point of the low impedance, that means through the capacitor, and thus capacitor will be unnecessarily overloaded with the harmonics power, and which may cause a premature failure of this capacitor. So, you have to keep in mind that once it is used with the frequency contaminated domain, then placing of the capacitor is very important to check the, to increase the longevity of the capacitor life, so that de-rating can be prevented. So, what generally we do, how the harmonics affects the capacitor? Capacitors are naturally, because Xc equal to 1 by omega c. So, higher is the omega, lower is the impedance. The capacitors are naturally a low impedance to high frequencies, and thus capacitor absorbs the high frequencies. Capacitor do not generate harmonics. So, there is an advantage of it. As capacitor absorb harmonics, the capacitor heats up and reduces the life of the capacitor. So, ultimately its insulations destroys and life get reduced. Voltage harmonic stress in the capacitor dielectric, and thus what happened, the reduce the life expectancy of the capacitor. Parallel combinations of the capacitor with the motor, parallel combination of the capacitor with motor or the transformer can cause resonant condition. That is also a challenging phenomena. We shall give some problem in your assignments, where there is a leakage reactance, and maybe you will turn on, because the capacitor was not there. So, you will switch it on lot of load, inductive load, to mitigate that you turn on the capacitor. The leakage reactance and the capacitor can set a particular frequency of oscillations, and thus if that frequency is close to 7th harmonic or something like that, then there will be a 7th harmonic resonance, and that may throw out the whole system out of gear. Let us see that. There is a sum of the nonlinear load that generate 5th harmonic, 7th harmonic and so on. So, you have a capacitors and you have a inductor. This may set to a particular frequency, and this frequency may be close to your particular harmonic it has been generating, and that harmonic will find a resonance into this tuned circuit, and it will set the resonance for the harmonics. This installation standard of the capacitor can magnify harmonic current in the network. That is one of the biggest disadvantage nowadays, because you have a harmonic generator and these oscillations will lead to the harmonic resonance. So, for this reason we know that what is harmonics ultimately. For the series harmonics it is XL and this is XC, ultimately this is an XC and XL. So, this will be the natural frequency of oscillations when XL equal to XC, and so that particular frequency should not be very close to the either 5th or 7th harmonic. So, for this reason capacitor resonance, this is a magnification of the harmonic current when standard capacitor added into the network. You can see that resonant point likely to amplify the harmonic, that is what I am saying, typically the 5th harmonic. So, depending on the leakage reactance of the transformer and the values of the capacitor. So, what happened here, this is the harmonic order. So, this is with the no capacitor bank. So, it is quite low, but what happened, so you have introduced 700 kilovar of the capacitive power, and you can find that it gives a resonance of 5th harmonic, and that is quite detrimental. So, ultimately it will find low resistance for the 5th harmonic. Similarly, this will, if you have 500 var, then the frequency will be shifted to the higher side. So, you will have the resonance around the 6th harmonic. Generally, if it is a 3-phase 3-wire system, 3rd harmonic is not present, you are safe. And then also if you increase further, it can be the 8th harmonic. So, if you increase the KVR compensation, there is a chance that it leads to the harmonic resonance, and that will have a lot of detrimental effect into the power system. So, for this reason power factor corrections with the harmonic we are now gradually avoiding, and we go for the solutions with the active devices for the STATCOM and other devices. So, we require to detune this network, force the resonance point away from the naturally occurring frequency, and we will make it something like 4.2 harmonic for the 50 hertz or 60 hertz depends. So, for the 50 hertz it will be 210 hertz, you have to tune like this. So, we control the impedance of the two elements, so that is basically the fax devices, and so we can control the value of the inductor, so that effective inductance can be effective impedance of these devices can be controlled, and you will be detune it from the fax devices, and thus it will not fall into the trap of the 5th harmonic or 7th harmonic. So, utility rate and the power factor correction. So, this is something is quite important. So, we know that most utilities penalize for the bad power factor, but there is a detrimental effect to it, and solution has to be provided by the STC. So, you generally have an inductor and with the thyristors in parallel, or you can generally have generally you can bypass this inductor, or you can allow this inductor to flow. Thereafter, you can have a capacitor, and thus what happen, a value of the inductor, you can control the triggering of these thyristors, and the value of the Xc, what you get essentially Xc minus XL, and where XL will be the function of the XL will be the function of this triggering angle, and thus you can change the effective value of capacitive inductor, so that it does not tune to the particular harmonic. If the consumer does not correct the power factor, the utility have to build more power plant, install new other large transformer, use large utility cables, wire, switch gear, etc., to handle the more KVA rating, many different rate structures across the country, and typically in India we are being penalized in industrial houses for having power factor less than 0.95. So, thousands of the customer across the country are unaware of this, that they are being penalized because of the low power factor, and ultimately we are coming to the commercialization of it, and nowadays prepaid meters to reduce the theft and other issues. So, you may not aware of that your current bill is eat out because of the low power factor. Now, this is for the industrial billing only, but it may be extended to the domestic billing up to some level. So, if you are staying in one society where you are having so many air conditioning and all those issues, then of course, you may be charged for it. Utilities recap the cost of providing reactive power in different way. One is KVA billing. Utility measures the bills every ampere of the current, including the reactive current, and thereafter real power demand billing with the power factor adjustment. Utility charges according to the kilowatt demand and adds surcharge of power factor, typically in the form of the multiplier of the applied kilowatt demand. Generally, this is the data I have taken from the USA. The KVA reactive demand charge, a directive charge use of the magnetizing power, for example, that is almost $4.5 per kVR, and two utility recently introduces, this data is from the Texas, are substantial power factor penalties for this much for power demand 0.95, and for in Tennessee 1.46 per kilowatt lagging, in this data is in 2004. So, most of the common power factors and the rate cut clause, that is very important for the power quality improvement for the consumer point of view, because you are working in an industry, they want to cut your electricity bills, and for this reason we require to place the capacitor rightly, but there is a hazards of placing capacitor, that you may have some frequency generated harmonic generated sources, and that may cause the resonance. So, we require to design properly the value of the capacitor. So, this is the penalties that has been discussing. So, due to the PF adjustment from kilowatt 2 to kilowatt 1 and distribution charges for the machine 1, nuclear decomposition charges and overall cost you have to bear, that is the total by month M1, M2, M6 by the, it is rupee or dollar or whatever it may be, ultimately phenomena is same. So, you have a transmission charges, you have a transition charges, there are transmission service charges, transmission cost recover factor, this all come into the picture and ultimately you require to calculate those values and you will be metered accordingly. So, what is very important now, the placing of the capacitor and its type. So, I have told you in little early that you have to have a variable capacitor, because you have some harmonic sources and that may corrupt this capacitor, and thus generally what happen, there are 3 options applying a power factor capacitor. A fixed capacitor individual motor of the motor rating, this one, and another may be the B, the automatic bank at main switchboard. So, you can switch it on according to the loading, and detune automatic bank, that is C, because you may cause a resonance with it with the main switchboard, and of course, this is A and this is also A. So, each has its own advantage and disadvantage, which you have understood from our discussions. Generally, this has been used so that it does not have a resonance with your power supply. Since it is a fixed, there is no point of control, so that sometime it may take the capacitive bar also. So, for this reason, this is the inferior solution. Next, since you can switch it on, for this reason this is little bit superior solution, because according to the load you can turn on these capacitors, and the best solution is a solution C, where you can also detune this capacitor so that it does not cause resonance with the adjustable power supply. So, just wrap up. So, main intention is a power factor corrections, side benefit, it recovers the sag, because if you terminate the capacitor, so it will recover the voltage sags and smaller I square R drop, corrections of the individual loads and the motors, but disadvantage is that overcompensations. If sometime if you have a fixed capacitor, then it may have overcompensate, you may have a capacitive bar not to be used for the nonlinear load, because you may cause a damage of the capacitor and may cause the resonance of the capacitor, unable to track minutes by minutes loading change occurring for the nonlinear feeders. So, we require to have a proper data to detune it, that is sometime always not possible, and thus you may lead to the resonance. And so, these are the capacitor bank, this is a courtesy of the Snyder. So, main benefit we have talked about all those things, and corrections of the entire MCC and the substations, and applications alert not to be used for the nonlinear load. That is something we require to keep in mind. If the nonlinear load is quite high, then capacitor bank, correction with the capacitor bank will not work. So, for this reason we require the anti-resonance automatic capacitor bank, which is the C type. This picture is courtesy to the same Snyder. The automatic capacitor bank where with a reactor in series, and it is been tuned to just below the fifth harmonic 4.2 to the 4.4 hertz, uses where nonlinear load is less than 50% of the total load, and transient free detune automatic banks for very sensitive network similar to the anti-resonance capacitor. It is same, it has been detuned to the for harmonic of 4.2 to 4.4, and it has a response time of less than 5 seconds, where nonlinear load is more than 50%. So, this is the way to put it, the electronic transient free. Ultimately, you have a thyristors, so that will turn on and turn off, thyristors and diode combinations, and you have an inductor and you have a capacitor bank. This is for the electronic switch transient free operation. I request the student to refer to the my fax devices courses. These entities are being discussed in detail. So, role of thumb of the power factor correction when nonlinear load is less than 15%, select the standard automatic capacitor. When nonlinear load is above 50% to 50%, select the detuned anti-resonant capacitor. When load is more than 50%, select active harmonic filter or the VAR corrections. When transformer KV or capacitor is around 3%, select anti-resonant or detuned capacitor. When soft starts are present, select detuned auto cap. So, thus I conclude my discussions here, and these are the few case studies which we will be discussing later. Thank you for your attention. So, we have discussed the problem of the power factor corrections and its mitigation for power quality issues. Thank you.